Good morning, everyone. Our chapter today is about bioequivalence studies. The first thing in this chapter is to understand the meaning of bioequivalence studies. Bioequivalence, it means comparing the bioavailability of a branded drug product to a generic drug product. You know, of course, from the previous chapter that a branded drug product, it means the first drug product developed for the new active ingredient. For example, for paracetamol, the brand drug product is Panadol tablet. After expiry of the patent of Panadol, of paracetamol, after the expiry of this patency, another companies can develop a generic drug product. We can find in the market many tablets and many drug products containing paracetamol now. All these drug products are generics. So the idea is to, before releasing the generic drug product to the market and administration by patient, we need to make sure that the generic drug product is having the same bioavailability as the brand drug product. To decide if the test and the reference or brand and the generic are having the same bioavailability or bioequivalent to each other, they should have the same rate and extent of drug absorption. Same rate and same extent. If they have the same rate and same extent of drug absorption, they are considered as bioequivalent. And you know, of course, that the word rate, it means how fast the drug is absorbed, and the word extent, it means how much absorbed, what is the absorbed amount of the drug, either from the generic or from the brand drug product. But there is another option, the test and reference, or in another word, the reference, the brand and the generic drug product could be similar in the extent but different in rate, and at the same time they could be considered as bioequivalent. Still, they could be bioequivalent. So the second case is that they could be having different rate and the same extent, but the difference in rate should be either intentional. So for example, if you are comparing sustained release generic tablet with immediate release brand drug product, so of course you are making your generic sustained to make it more convenient to the patient. The patient will take it one time daily instead of 3 times daily. So it's intentional. If it is intentional, so it is accepted. Here the difference in rate is accepted because it is intentional. It has a benefit to the patient. And at the same time, the difference in rate shouldn't affect the safety and efficacy of the drug. So for example, if the patient is having migraine, the patient need fast action. In this case, don't make sustained release. But efficacy, if the efficacy is maintained, safety is maintained, so the difference in rate is acceptable. But the only thing which is not acceptable is the difference in extent. Extent is very important. So again, we have two cases. If the drug brand drug product and the generic drug product are having the same rate and extent, again they are considered bioequivalent, and that is by default. But and also if they have the same extent but different rate, in this case it could be acceptable if the difference in rate is intentional, and at the same time this difference doesn't affect the safety and efficacy of the drug. Our next question is how to make bioequivalent study. We should have healthy volunteer. Bioequivalent study is not happening or not done on patients. It should be done on healthy volunteer. We should have two groups of healthy volunteer. This blue group, for example, will take the test drug product or the generic, and this green group will take the reference drug product. Once they administer the tablet or the capsule, this time is considered as time 0. That is the time of administration. After administration, we have to take plasma samples or urine samples at different time interval. For example, after 0.5 hour from administration. If the patient taking the medicine at 10 a.m., so at 10:30 we have to take a sample from every volunteer. Sorry, not patient, of course. From every volunteer. After 1 hour also at 11 o'clock we have to take another plasma or urine sample. After 2 hours at 12 o'clock, after 3 hours at 1 o'clock. So at each time interval we have to take either plasma or urine sample. After taking these samples, we have to extract the active ingredient from this sample, from the blood or plasma sample, and then inject it into HPLC, analyze the amount of drug absorbed at each time interval. So at the end we will have time against CB, concentration of drug in plasma at each time interval. That is a plasma concentration time curve. If it is oral, the curve will be like that. So we can calculate area under the curve. We can determine the Cmax and Tmax of the drug. Then we need to understand now the definition of the word of reference standard. Reference standard is the innovator, is the main pharmaceutical product produced for the first time for a new active ingredient. As we mentioned before, we have an example of paracetamol. The reference standard for paracetamol is Panadol tablet. The reference standard for captopril could be Cabotin or Cabozide. The reference standard for Donepezil anti-Alzheimer is Aricept, Pfizer company. So for every active ingredient there is an innovator or reference standard, and both the generic and the brand should be taken by the same route of administration. For example, you cannot compare tablet with injection. You have to compare tablet with tablet. If there is no reference with the same dosage form, there is no tablet, for example, and you are making tablet for the first time, you can compare it with capsules, but at least they should be taken by the same route of administration. Also, they should have the same dose. If there is a difference, there is allowance and difference only 5%, not more than that. So again, the bioequivalence study should be done on healthy volunteer, not patients, and their age should be between 20 to 50 years old, and weight, average weight from 54 to 91 kilogram, and they have normal body fluid. They shouldn't have dehydration, they shouldn't have ascites or edema, because all that will affect everything in pharmacokinetics, starting of course from distribution, and this will may reflect on absorption and elimination also. We have 4 study designs: the fasting study, food intervention study, multiple dose or steady state study, and the crossover design, and we will take them now one by one in much details. The first type of the study design is fasting study. In this case, the healthy volunteer should be fasting overnight, at least 10 hours before administration, and should remain fasting for 2 to 4 hours after administration. So fasting here is extended before and after administration. Before administration, at least 10 hours. After administration, 2 to 4 hours. The second point here, in all study designs, no other medication should be taken 1 week before the study, to avoid, of course, drug-drug interaction. And this point is not in fasting only, fasting, food intervention, and any other design also. Blood sample or urine sample collected at different time interval, and as we explained before, we have to plot plasma concentration time curve, and the study also extend up to 3 to 5 t-half of the drug with a minimum of 24 hours. Minimum of 24 hours. What is the meaning of that? For example, if the drug is having 1 hour t-half elimination, 3 to 5, let's take 5 t-half. 5 t-half for 1 hour, so it means 5 times 1 equal 5 hours. So the study should extend up to 5 hours. We have to take sample up to 5 hours. But there is another condition, is the minimum is 24 hours. So for a drug having a t-half elimination of 1 hour, we should have the study 24 hours. Take samples up to 24. But if we have a drug having a t-half of 8 hours, t-half elimination 8 hours, so 8 times 5, it will be 40. So the study should extend at least 40 hours. In this case, of course, we can extend it to 2 days, up to 48 hours. The second type of the study design is food intervention. In food intervention, the healthy volunteer should remain fasting also overnight. So don't think that the fasting is required only in the fasting study. Even in food intervention, the healthy volunteer should remain fasting overnight, at least 10 hours, but he will take a meal 30 minutes before dosing, standard meal, not any meal. So we are making sure that the healthy volunteer, all the volunteers are taking the same meal. If there is an interaction, it will be unified across all the healthy volunteer we have, to avoid also the effect of different food constituents to the drug on the drug absorption. The third type of the bioequivalence studies is multiple dose study. And instead of taking a single dose, the healthy volunteer here will take several doses, maybe taking 4 doses like in this graph. So the volunteer will take the first dose, the curve will go up and down like that, and then after 24 hours, volunteers will take the second tablet. After 48 hours, the third day, starting of the third day, every volunteer will take the third tablet, and at the start of the fourth day, every volunteer will take another tablet. So that is an example of multiple dose study. The advantage of this study is having higher plasma concentration. If you observe from the previous curve that the plasma level is going up like that, that is the first tablet, the second tablet, the third tablet, so Cmax is going up. So if you have a problem in analyzing the drug in plasma or in urine, you can observe here that Cmax is going up because of the accumulation of the drug inside the plasma, for example. But we have disadvantage. The disadvantage here is that you need to take more sample from every volunteer. You have to pay for every volunteer for the time they are spending here. They are instead of spending 1 day, every volunteer will spend 4 or 5 days in the study. So it will cost more and more. And also taking more plasma samples, they will complain, they may be affected, and also analyzing this sample will cost more money. Design number 4 is crossover design, and that is the most important one. For example, if we have 6 subjects, of course the word subject here, it means volunteer. If we have 6 healthy volunteer or 6 subjects, 3 out of these 6 volunteer will take the test, and the remaining 3 will take the reference drug product. So the first volunteer number 1, 2, and 3 will take the test drug product or the generic, and the volunteer number 4, 5, 6 will take the reference. After 1 week, for example, and we can call this period as washing out period. After a washing out period of 1 week, we will have another study period 2. In this case, in the study period 2, volunteer number 1 and 2 and 3 will take the reference. So in the first period they took the test, but in this period will change, they will take the reference, and volunteer number 4, 5, and 6 will take the test. So what is the advantage here? Here, if you can observe every row in this table, volunteer number 1 took already the test in the first period and took the reference in the second period. Same for volunteer number 2 and 3. Volunteer number 4, 5, and 6, every one of them takes the reference in the first period and then takes the test in the second period. So for every volunteer, now he took reference and test. So this will eliminate any variation between volunteer and each other, because everyone is having maybe different weight, different physiology inside his body, and all that will affect drug absorption, distribution, and elimination. But if you are comparing the test and the reference drug product within the same volunteer, every volunteer is taking the reference and the test. So in this case, we are eliminating the inter-subject variability. The word inter-subject variability, it means the difference between volunteers and each others. The second point here, what is the meaning of the washout period? The washout period, there is a condition that we need to know. This washout period should exceed 5 half-life with a minimum of 1 week. So if the drug is having 1 hour T-half elimination, 5 half-life, it means 5 T-half, it means 5 hours, 5 times 1. But we will not make it 5 hours, we'll make it at least 1 week. But if there is another drug having T-half elimination 2 days, so 2 days times 5, it will be 10 days. So the washout period for this drug will be 10 days. What is the idea of that? The idea is to make sure that the body is washed out of the drug. All the drug is eliminated. All the drug administered in the first period is eliminated totally from the body, and it will not affect the concentration in the second period, where the patient will take the other drug product. And at the end of this slide, as we mentioned before now, that every subject is taking the reference and the test. So each subject, each volunteer is acting as its own control to reduce subject-to-subject variability or inter-subject variability. After taking the sample, we need to analyze it, so we have to have a valid analytical method, and that is called validation of the analytical method, and it is different from pharmaceutical validation of production. Validation of the analytical method, validation of the method of analysis by HPLC or by LC mass spectroscopy. This method should be accurate. Accurate, it means it can give the right value. If the concentration actually is 10 nanogram per milli, so the method really will give you 10 nanogram per milli. It will not give you 5 or 15 or 17. It should give you the right value. And the word precise, it means if you inject the same sample several times in the equipment, in the HPLC, it will give you similar results. So if it is giving you in the first injection 10 nanogram per milli, if you inject it again, it will give you 9.8. Third time, it will give you 10.2. So it's very near, very close to each other. That is precise. But if we inject the sample first time and it give you 10, if you inject again sample from the same container, same vial or whatever, same test tube, you inject a second sample and it give you 8, third time it give you 13, it means that your method is not precise. There is no repeatability. And the third one is sensitivity. Sensitivity, it means you can detect the smallest concentration in plasma or urine. Your lower limit of quantification is very low. You can detect down to 1 nanogram per milli. That is the ideal case scenario. The second type, after analysis of the drug, you will make a plasma concentration time curve, and you need to detect or determine the area under the curve, Cmax and Tmax, and of course the most important criteria is AUC. The third type of analysis, after analysis with equipment, pharmacokinetic analysis, we have a third type, which is statistical evaluation. If you are comparing Cmax of the test to Cmax of the reference and they are similar or different, how to decide that? You should decide based on statistical analysis. For example, if Cmax for the test is 8.5 and Cmax of the reference is 7.9, is it similar or different? If this difference is significant difference or not a significant difference, you cannot decide by yourself. You have to depend on a statistical test, and mostly we are using one-way ANOVA, analysis of variance test. We have another question here. Shall we make a bioequivalence study for every generic product? The answer, no. We shouldn't do bioequivalence study for every generic product. Sometimes it is a must to do. For some generic product, it is a must to do. It is a must to establish a bioequivalence study, and we will understand in the coming slides what are the cases that in which we have to make a bioequivalence study. But in some other cases, we can waive the generic drug product from the bioequivalence study. We can make another type of study other than bioequivalence, which is called Bioequivalence study. And the word Bioequivalence study, it doesn't mean that you will not do anything. You will do another alternative other than bioequivalence, which is the solution. So in Bioequivalence study, you will compare the solution of the active ingredient from the test drug product to the solution of the active ingredient from the reference drug product. So in some cases we have to make bioequivalence study. In some cases we can waive the generic from bioequivalence study and we can make the solution study. And the solution study is called Bioequivalence study. So let's understand together what are the criteria for establishing a bioequivalence study. To establish why we need a bioequivalence study, if the drug is having a problem like what? For example, if a drug is having a narrow therapeutic ratio, you're afraid from the drug if more drug is absorbed, so the plasma concentration Cmax may exceed the minimum toxic concentration. So the drug will be toxic. And for example, if the drug is absorbed to lower extent, less than the reference, so the Cmax will become lower or less than the minimum toxic concentration. In this case, the drug from the generic drug product will not become effective. So really, if the drug is having a narrow therapeutic index, so that is very dangerous. We have to make sure that Cmax and AUC in case of the generic is similar to Cmax and AUC in case of the reference drug product. The second point is criteria related to the physicochemical characteristics of the drug. If the drug is having any problem related to solubility, related to dissolution, having a polymorphism, maybe every polymorph is having a different solubility, different dissolution. So that is the case here. So first example of the physicochemical criteria is the drug is having low solubility. So we have to make sure that the drug dissolve from the generic with the same extent from the brand, and also the solution rate. If the drug is having very slow dissolution rate, less than 50% within 30 minutes, so we have to make sure also that the excipient present in the generic will not affect the drug dissolution. Particle size, if the particle size is critical in dissolution, for example, increasing the particle size from 1 micrometer to 2 micrometer may reduce the dissolution rate to 10%. So if the difference in particle size has a significant effect on dissolution and solubility, we have to make sure that the test and the reference are having the same solubility and dissolution and the same absorption rate. Otherwise, you don't know the particle size of the active ingredient in the generic and the particle size in the reference if they are similar or different. So in this case also you have to establish or to make a bioequivalence study. Also polymorphism. For example, if the drug is having two polymorphs, polymorph A and polymorph B. Polymorph A is soluble, polymorph B is insoluble. Maybe the reference drug product is having the polymorph A, which is soluble, while the generic drug product, due to the manufacturing condition, polymorph B is formed, which is insoluble. So in this case, the solution and the absorption will be different. So in this case also, we need to make a bioequivalence study. A last point or last example here, if the ratio of active ingredient to excipient is very low, or if we can tell it with the opposite way, if the ratio of excipient to the active ingredient is very high, for example, more than 5:1. For example, if you have the active ingredient dose in each tablet 1 milligram and you have 200 milligram excipient, so you can imagine the ratio here is 200 divided by 1, 200 to 1. So much excipient and very small amount of active ingredient. There is a great opportunity of interaction between the drug and the excipient. And you know, this interaction may affect everything. May affect stability, solubility, dissolution, and all other pharmacokinetic, all other physicochemical characteristics of the drug. The third case in which we have to make a bioequivalence study if the drug is having a pharmacokinetic problem. Pharmacokinetic problem, it means problem in absorption, distribution, metabolism, elimination, or even at least stability inside the GIT. Let's take examples about that. First one, if the drug is having problem in absorption. For example, absorption from certain segment inside the GIT. Many drugs, as you know, that many drugs can be absorbed only from the first part of the duodenum, like cimetidine and ranitidine. So these drugs, now both of them are stopped from the market, not because of that, because of other reasons. But many other drugs could be absorbed only from the first part of the duodenum. So you want to make sure that your tablet, the tablet of the generic drug product, can deliver the drug or can release the drug before the duodenum, like the brand. If your generic tablet release the active ingredient after the duodenum, nothing of the drug, nothing of the dose will be absorbed. The second example, if the drug is having poor absorption, less than 50% compared to intravenous, so if the drug absolute bioavailability is less than 50%. The third case, if the drug is having very rapid metabolism, the drug is very fast taken and extracted by the liver and metabolized into another compound. the last example, if the active ingredient is unstable in the GIT, for example, if it is unstable in the stomach, degraded in the stomach, so you have to make sure that the generic drug product is protecting the active ingredient from the HCl, and the enteric coat of the generic is good, same as the brand drug product. So after understanding the criteria for establishing a bioequivalence study, let's talk in this slide and the coming slide about criteria of waiver of bioequivalence study. It means no need to make a bioequivalence study. The drug doesn't have any problem. We can make only biowaiver study, as we mentioned, which is the solution only. To make a biowaiver study, what are the criteria for that? If the drug is good in everything, good in the solution and absorption and all other criteria. First example, if we have, for example, here oral solution. In case of oral solution, the active ingredient is already soluble. So if it is already soluble, most probably it will be absorbed with the same rate as the reference. Nothing will hinder its absorption. And you know, bioavailability from any oral solution is very high. Second thing, if we are making a generic which is intravenous solution, of course in intravenous solution there is no absorption, there is no absorption phase. The drug is injected directly inside the plasma or inside the bloodstream. So if there is no absorption phase, how to compare rate and the extent of drug absorption? There is no even absorption. The third and fourth and fifth example are talking about locally acting drugs. Either locally acting drug which is applied on the skin. If the drug is acting locally, so you don't care about the amount of drug absorbed. You need only the drug on the skin. Even if certain amount of drug absorbed, that is not important. Also, if the drug is inhaled and acting locally inside the lung, that is also the same scenario. So the drug is acting locally in the lung, you don't care about the amount absorbed. Point number 4 is here we have oral tablet, but the active ingredient is acting locally inside the GIT. Like for treatment of ulcerative colitis, we are taking active ingredients which dissolve in the colon and acting locally inside the colon. No need for these drugs to be absorbed. Even if it is not absorbed, it will be better to avoid any systemic side effect. So it will act locally inside the colon and treat the inflammation present inside the colon. So we have here 5 cases. If we have oral solution, which is by default having very high bioavailability. If we have intravenous solution, which is already having 100% bioavailability again by default. And if we have a local medicine, locally acting drug, either topically or by inhalation or even by oral administration. For biowaiver also, you can biowaive or make waiver for dosage form which is not acting, which is not solution, oral solution, not injection or intravenous solution, and not acting locally. You can make waiver even for solid oral dosage form, like tablet and capsule, and the active ingredient is not acting locally even inside the GIT. But in certain cases, these exceptions are depending on the drug solubility and the drug permeation and the drug dissolution rate. So let's talk about them one by one. If the drug by default is highly soluble and highly permeable, like class 1 drug according to biopharmaceutical classification system, you know that we have 4 classes, class 1, 2, 3 and 4. Class 1 by default they have high solubility, high permeability, and solubility of course will lead to high dissolution rate. So for class 1 drugs could be biowaived from bioequivalence study, and we can try the dissolution only in vitro, could be enough, even if they are present in oral tablet or oral capsule and they are acting systemically. But there are more details about the meaning of the word highly soluble. The word highly soluble, that it means that the highest dose strength, the highest dose present in the market, for example, if we have, for example, Augmentin 500 milligram and 1000 milligram, so the 1000 milligram is the highest dose strength. The highest dose strength, which is 1000 milligram here, can dissolve in less than 250 milliliter water at different pH. This water, we should try 250 milli with pH 1, with pH 2, with pH 3, up to pH 7.4 or 7.5. And of course, you understand why we are selecting this range, because that is the pH range of our GIT, starting from pH 1 or 1.2 in the stomach up to 7.4 in the ileum. So if the highest dose of the drug can dissolve in less than 250 milli of body fluid or GIT fluid of stomach or small intestine or large intestine, it means that the drug is highly soluble. And the drug should be highly permeable. Its absolute bioavailability should be more than 90% compared to intravenous. And to decide if the drug is rapidly dissolving, it means that more than 85% of the dose should be dissolved within 30 minutes in USP apparatus 1 or USP apparatus 2.